I'm Yilun Wang from Pengfei University. Today, I'm very pleased to introduce our latest work, DeepCAT, a cost-efficient online configuration and tuning approach for big data frameworks. In order to adapt to variety scenarios, big data frameworks such as HDFS, Spark, and Flink usually provide a large number of configuration parameters for developers. Spark has more than 400 configurations, and many of them are performance critical. Incorporated configuration may lead to low performance, massive waste of resources, and even execution failure. So tuning configuration parameters is essential but challenging. The reason is that, first, complex relationships between parameters and performance. Second, high-dimensional configuration space. For example, we tune 32 continued configurations, which range from 0 to 100. The exploration space is far greater than 32 to the power of 100. Third, very heavy configuration evaluation cost. Each execution time of big data application ranges from minutes to hours. Existing all-in-tune methods have limitations. First, search-based methods do not take advantage of past trails and learn from scratch. That is very time-consuming. Second, machine learning-based methods rely on massive high-quality samples that is hard to obtain and have a poor adaptability to workloads and hardware environments. Recently, reinforcement learning-based methods is popular. It uses try and error strategy and rewards feedback to encourage learning. It do not rely on massive high-quality samples and is adaptive with environmental changes. We show the workflow of DRL-based tuner that are composed of offline training stage and online tuning stage. In offline training stage, agents interact with the environment. All the samples are stored in the memory pool. In online tuning stage, agent is responsible for fine-tuning the pre-trained model to recommend the configurations. However, current DRL-based methods are not practical enough. The reason is that, first, the problem of overestimation in traditional DRL algorithms. Second, the inadequate usage of good samples in experience replay. Third, neglecting the estimation of online tuning stage that causes high tuning overhead. We summarize our goals. First, to accelerate offline training process by efficiently utilize real but valuable samples. Second, to reduce online tuning cost by utilizing the optimal configurations. Third, to optimize the performance of different big data application scenarios. We translate configuration on tune problem into a DRL formulation. Agent is our tuner. Big data system is the environment. States refer to the system resource monitor, and action are the value of configuration that needs to be tuned. And then we design a reward function according to the performance improvement compared to the expectation. Here, we show the cumulative distribution function of random configurations. We observe that it's easy to find a better than default configuration, but the close to optimal configuration are far fewer than the optimal ones. Only 4% of configuration are close to optimal. Experience replay used by the policy IO. Sample transition from the memory pool in a totally random way. It fails to recognize the important transition. Prioritize experience replay. Use TD arrow as priority of transitions to gain more information about environment, but is not suitable for dense report. So we propose RDPR, a reward-driven prioritized experience report. We first divide transition into two categories, low reward and high reward, and utilize two memory pools, P low and P high, to store them. When training starts, we isolate sample-specific number of transitions from two memory pools to train the AI. We show the effectiveness of reward-driven prioritized experience replay by plotting offline training process of DRL tuning results. The figure shows the best execution time in different number of iterations. As shown, RDPER speed up offline training by a factor of 1.6 times and is improved the configuration performance. Because RDPER take advantage of valuable but sparse high reward samples. In the implement of DDPG, a popular algorithm in DRL-based tuning, we found that the overestimation of value estimates of DDPG inevitably appears in our early tuned environment because of the insufficient exploration. Figure A shows the obvious overestimation of value occurs in the learning process. The deviation is aggravated with learning process. Figure B shows that portrayed DDPG cannot find near to optimal configuration form. So our solution is to utilize TD3 algorithm instead of DDPG in DeepCAT. As we can see in picture, TD3 uses two critical networks to estimate the value of action. A smaller one will be used to update the active network. Therefore, TD3 will address the value of estimation problem. Besides, it also performs target policy smoothing regularization as well as delaying policy updates to provide a more stable training process. When we tune application online, DeepCAT needs to perform several online tuning steps to fine-tune the model to adapt to the real environment, but this process still has to evaluate the time-consuming suboptimal configuration and is too heavy cost. Since traditional DRL method totally neglects the cost of each online tuning step, it's challenging for our algorithm to obtain an estimation of current actions. Here, we show the Q value of TD3 and the relationship between its real reward. As we can see, Q value shows a very similar trend with real reward and will recognize the suboptimal configuration. Motivated by this, we designed Pengfei algorithm. It estimates the quality of online recommended configurations based on twin rating and replace the suboptimal configuration with Gaussian noise until the near to optimal one is found. We conduct online tuning experiments with the results. We can see with Pengfei optimizer, DeepCAT save much online tuning time and better configuration. We can see the latter four steps are regarded as suboptimal configurations and optimized to better one. It demonstrates that Pengfei optimizer actually captures the suboptimal configurations and is able to generate better one current than itself. Putting them together, we design a configuration tune system, DeepCAT, which is composed of offline training stage and online tuning stage. DeepCAT uses TD3 with reward-driven prioritized experience replay to offline train DRL models. When an online configuration tuning request is correct, U3 output an action according to user states. In the Pengfei optimizer, we estimate the real execution time and optimize original action better. When the number of steps which the constraints or the total tuning time exceeds the budget, DeepCAT will terminate and report best configuration ever found. In the experiment, we optimize a big data pipeline, including Spark, Yang, and HDFS in a 3-node cluster, and we tune 32 configurations on them. We use 4 workloads: word count, parasort, PageRank, and k-means with 3 different data size and bench. We compare the default configuration and the 2 baselines, CDB tune and All-in tune. We first offline tree them and we conduct 5 online tuning steps according to CDB tune. And the 5 tuning steps is a trade-off between exploration and exploitation. And then we record the best configuration, execution time, and the online total tuning cost. We evaluate the performance speed up of DeepCAT. Figure shows the speed up over default in 4 workload with 3 different data sizes. DeepCAT perform best, and the average speed up over CDB tune and All-in tune is 1.45 times to 1.65 times. The reason is that the Gaussian process regression model in All-in tune is too simple to capture the complex relationships between configurations and performance. CDB tune works better in high dimension, but we don't consider the effectiveness of successful historical experiments. We evaluate the online tuning cost of DeepCAT. We reduce 25% much online tuning time on average and up to 50 compared to CDB tune, and 40% on average and up to 53 compared to All-in tune. Because DeepCAT optimizes for optimal configurations during online tuning stage. Besides, we find All-in tune takes the most time for recommendation because we can use traditional machine learning methods. And the DeepCAT and the CDB tunes can be neglected. Now, we evaluate the effectiveness of the tuning cost per string. As shown, DeepCAT is able to find a better configuration with much less cumulative tuning time for all the workload, and is able to compare tuning in few steps. Next, we evaluate the adaptability varying different workloads. Use model trade on other workloads to recommend PageRank workload. As you can see, DeepCAT perform much better than CDB tune and All-in tune, even if they are trained on PageRank. Second, we find the model from parasort to PageRank perform worst because of the most different workload characteristics. The underlying reason that parasort is based on web and reduced process, that is a CPU and memory intensive, while PageRank is based on iterative selection. Last but not least, we find that if reinforcement learning have a better adaptability than machine learning method, we then show the strong adaptability in different hardware environments. We use the model trained on cluster A to tune Spark applications. Other cluster B. We can see DeepCAT is much better than CDB tune and All-in tune. We conclude our work. We propose a cost-efficient online configuration of the tuning approach named DeepCAT based on deep reinforcement learning for big data frameworks. To reduce online tuning costs, DeepCAT utilized TD3 algorithm instead of DDPG to elevate value over estimation. And we design a global reward-driven prioritized experience replay chainism to fully utilize the real but valuable experience. And we propose Pengfei optimizer to estimate the execution time of each action and optimize the suboptimal one. Experimental results based on local Spark cluster and high benchmarks application show the effectiveness and the efficiency of DeepCAT compared with CDB tune and All-in. Thank you for listening to my talk. If you have any question, welcome for asking.